And he's now a postdoc at Waterloo. He's going to speak about tensor decomposition algorithms.
For the invitation. I hope this is like big enough for everyone. So I'll be talking about tensor decomposition algorithms, why algebraic complexity. So basically, these are the tools we developed for studying reconstruction problems while studying algebraic circuits, and that has applications in learning for decomposing tensors, which is what I'm going to talk about today. So again, to start with, we have a tensor tau. Let's call it a I1, I2 dot ID, and let's say this element in if N1, N2 is being a bit lazy and not writing the indices here. Good. So we saw a bunch of ways to look at tensors. We look at as a bilinear map, as an array of numbers, and also Kevin mentioned as a trilinear form. And that's how what I'm going to look at tensors like. For me, tensors are set multilinear polynomials. And let me define how I write that polynomial for a tensor tau. So for a tensor tau, my f tau of x would be, I'll just basically take different sets of variables and put a signature of the entry as a monomial. So for the entry AI1, I2, ID, I will just put x1, I1, x2, I2, dot x d, ID. Here x, let me just look at what are the variable sets. Let me write it as small. So look at my variable set x. It's a disjoint union of I in D of xi, where xi comprises of xi1 dot up to xi ni. And these kinds of polynomials are called set multilinear polynomials because if you look at any monomial, there is a variable partition such that each monomial has exactly one variable from each partition. Okay, so that's how we look at tensors, and it's helpful to look at it like this for the following reason. So there is an observation that if tau is a rank k, has a rank k decomposition, let's say VI1, VID.
Excuse me, it's this to be on the same page.
Right.
So you're looking at symmetric tensors.
No, I'll also talk about symmetric tensors, but this is for general tensors. That's why there is this variable partition. So I've added this extra index to basically put a signature of which entry was there. Like, maybe I should just give an example. Oh, you got it? Good. So if your tensor decomposes like this is equivalent to saying that your polynomial f tau of x has the following decomposition. Okay, what do I mean by this? Good. And this xj is the same xj I defined here. Awesome. So what does Lij correspond to Vij? Is basically how do you write a vector as a linear form? The canonical way. For example, if your vector is 2, 3, 5, and you just write it as 2x1 plus 3x2 plus 5x3. So that's the connection. And it's very easy to prove this. Basically, you observe it for k equal to 1 and then extend by linearity. And for k equal to 1, the proof is essentially follows by observing if you multiply variable disjoint linear forms, it behaves exactly as tensor product. So that's the connection of general tensor decomposition to writing your polynomial f tau in the following manner. So you can do the same thing for symmetric tensor as well. Let me quickly write this. So if your tensor is symmetric, let me define f tau sim, writing the same thing but just dropping these indices. So you have a I1, a I2, a I-D, and you write xi1, xi2. And if your symmetric tensors has decomposition like this, if observation 2, if tau sim can be decomposed as d times, this is equivalent to writing your polynomial f tau sim as powers of linear forms. Again, these are very standard connections.
Sorry.
Yes.
So f tau sim is defined for any tensor. You don't need the.
No, it's symmetric. I'm defining it for a symmetric tensor.
Tau is your tensor.
Right. So
tau does not have to be symmetric.
right.
Tau is a tensor, and you define f as
And f tau
sim,
right.
It's a polynomial, and then if tau is a symmetric tensor,
then I define f tau sim. Okay. Awesome. So let me talk about what are these models in arithmetic complexity terminology. Wait, let me just write here. Okay, so this model, for instance, for a variable partition is referred as set multilinear depth 3 circuits. It's called set multilinear depth 3 circuits. Let me just write K to denote the top panel. These are well-studied objects in algebraic complexity. Even generalizations of these objects are studied. For example, if we get away with this variable disjoint structure, these are the general depth 3 circuits, and so on and so forth. Awesome. So, and this object is known as the sum power sum circuit. And what these connections tells us, if you can learn or if you can decompose your polynomial in this following representation, that is equivalent to decomposing the tensor. And the problem in algebraic complexity is given black box access to a polynomial f, write a circuit. So this problem is known as arithmetic circuit reconstruction. You can talk about what's the complexity of f, and then you can define reconstruction for various arithmetic circuit classes. So these two problems are proper learning or reconstruction for set multilinear depth 3 circuits and sum power sum depth 3 circuits. And this problem has been studied for various other classes as well. Let me just point a few. So it's been studied for sum power sum, set multilinear depth 3, multilinear depth 3. So I'll talk about these two things. This Ben Lee will talk about on Thursday, and another interesting class is sums of powers of low degree polynomials. I'm guessing Tim will talk about this on Thursday. So again, there are various models and there's reconstruction problem for them, and all of them are, at least for these special models, they're quite intricately linked with decomposing tensors. And so that's all I wanted to talk about reconstruction, and rest we can just
What did you write there?
sum power sum, that's exactly the same. This is
Sum and then
this is set multilinear. I don't want to write set multilinear, right? Awesome. So let me just write the main theorem I want to show today. So
can you lift the other boards?
oh, will it go up? Oh no, this stationary. I can maybe write this one.
Six.
Okay, yeah. Well, I mean, they're very strong.
Right. Okay, I'll just. Oh wow. Distracting. All right, so the theorem This is joint work with Shubhangi Saraf and Ilya Volkovich. It says that if this is for general polynomials, and then we'll instantiate for tensors. So if f can be written in the following way, I equal to 1 to k Lij xj. We don't know. Then given black box axis. By black box axis means you can evaluate your polynomial at any point you want in the field. When black box axis, we can find a set multilinear representation. So we can find a representation like this, not exactly this one, something close to it, but it will be optimal as well. In poly n d to the k to the d to the k to the order 1, and then k to the k to the order 1. For this talk, the field is complex, so otherwise this time complexity depends on the field, but this is for complex.
This RCPS in the end.
RCPS.
On the right.
Oh yeah. Oh, I see. Oh. Right. So what a corollary of this is, we'll instantiate for the polynomial f tau. We get that we can decompose k tensors in this amount of time. And this is might look very odd at first, because just to write the tensor, you will need approximately n to the d bits of information, and this seems to be not even taking into account n to the d. And this is because we are just looking at evaluations of the polynomial f tau. We're not even looking at the whole tensor. So we'll just look at the evaluations of tensors, and so we don't have to look at these many evaluations. Just something around these many evaluations suffices, and the reason is because rank is so low. So this is what we'll try to prove today. So let me first start by giving some warm-up of how we use algebraic complexity to, let's start with a like a well-known result. So we'll first focus on this model, which is equivalent to decomposing symmetric tensors of rank k. This is equivalent to, given a polynomial element to the d, I to the d. So there's a special case of this which follows by Jennrich's algorithms. So it follows by it. So it's the following thing: if your tensor is summation I equal to 1 to n vi tensor vi such that v1 up to vn are linearly independent, then in poly n time we can decompose tau. So just the Jennrich's algorithm works in this setting, and you can apply that, but we want to do it using algebraic complexity. So we'll look at f tau, in particular f tau sim, and try to work with that and apply some algebraic tools. So let me review.
What do you mean with decompose?
We will write it as, we give exactly this decomposition. It will be unique in this case, actually. It follows from Jennrich's. It will also follow for our argument that the decomposition
But again, in this black box model.
in the black box model. But you can get the black box model if you have the whole tensor, right? You can. Oh, actually, this is low degree. So if degree is low, you can. There's not much difference. For instance, look at the time complexity. If these three, then you will at least get the n time complexity.
But you're given tau, but you're not getting the VIs, right?
Yes. This is unknown. That's what we want to
But
find.
unknown.
Yes.
But you're allowed to evaluate tau.
Yes.
right?
Yes.
In your map. And then using these evaluations, you can find the VIs.
Exactly.
Yeah.
So I'll prove. Yeah.
And we're putting in the evaluations.
Yes. I mean, you can do this for general tensors. For simplicity, I'm just doing for three-dimensional tensor. But the proof actually just scales. So just recall, we can look at f tau sim. I'll just drop the tau sim for now. And we have the L1 cube plus L2 cube dot Ln cube. And the polynomial L1 Li's are linearly independent. So this is the setting in language of polynomial. And we want to learn this decomposition. We know one exists, we don't know how it is. So
what's the dimension of this tensor? The format?
yes, okay. This is FBI is okay. So we have black box access to this polynomial f. We look at the following matrix. It's known as Hessian of a polynomial f. What is this? You look at second order partials. Fill it up. So you have del x1 dot del xn. Again, you have del x1 dot del xn, and the ith jth entry is if you have black box access to f, these are just first, second order partial derivative. You can get black box access to all the partial derivatives.
Excuse me, so this lemma works only for rank n.
Yes.
I mean, n is the same as the
Yes.
dimension.
Yes, it
Cannot
could
be smaller.
right.
So you
It can be smaller actually, but I just wanted to write something concrete which I can prove. So I'm just writing a special case. I mean, even if it's less, you have to do some more manipulations and you can solve that case as well. But what you need is this linear independence condition. So this n can be smaller. So as it turns out, that this Hessian matrix factorizes in the following way. So this is also equal to, just write it. Do x1 dot xn and L1 dot Ln, and followed by diagonal matrix, the transpose of this matrix. This is just by observation. So if you have black box access to this, if you have this matrix Hessian, then you can look at the determinant of the Hessian, and if Li's are linearly invertible, so let's call this matrix A, and this will be A transpose. So we have determinant of Hessian, I'll just abbreviate for now, of F is equal to det of A whole square times product of the linear forms. And if my linear forms are linearly independent, it's easy to observe that these matrices will be invertible. So this determinant will just be a field constant, in particular non-zero field constant. So if we have black box access to all the entries, we'll have black box access to this product because we can compute the determinant on top of it. And we can just apply the black box factoring algorithm of Karl'topf and Traeger. So apply different Traeger black box factoring to get black box access to each irreducible factors, and these are just linear forms, so you can learn them. Apply, let's say, in particular sparse reconstruction to learn LIs, and that was your goal all along. You wanted to just learn LIs. And if you look at this slightly carefully, this is also implicitly giving a proof of uniqueness of such decomposition, because the Hessian was just a property of the polynomial, not of this decomposition. But the determinant, this is a unique factorization of this determinant, and since it's unique factorization, all representation looks like this. So it gives that into a particular, this decomposition, if Li's are linearly independent, is unique. So again, this is a warm-up to like the tools we use to get learning.
How do you get black box access to the hashing?
Okay. So we have black box access to each individual entries. This is because up to some constant order partial derivatives. If you have black box access to a polynomial f, you can get black box access to its first or second or third order partial derivative. The time complexity is exponential in terms of the order of the derivative. But for first and second is fine.
Set is powers.
No, this is no, I think this is even before.
I mean, you can show it. I mean, for example, if it's multilinear and you want to derive with respect to x1, so you just evaluate it
Yes.
like 1 minus evaluating at 0.
Yes. Since it's multilinear, it's even easier, but we can do it in general. Yeah. That's true to all the techniques here. There are maybe much easier way to do it for multilinear polynomial. I'm just using the general tools. Awesome. So I gave you one warm up, but that's not what.
What was the order again of the algorithm? So you have.
Oh, so you just have to do factor. You have to. It will be poly n because.
I don't know, sorry, what is the section thing?
Oh, the algorithm is make the Hessian matrix, compute its determinant, black box, factorize it using black box factoring, and look at the linear factors and learn them. So I think what I'm glossing over is one step I should just write. If you have, let me just write a theorem. Let me write informally.
So so the determinant S is a polynomial.
Yes. Yes.
Then you factor it.
Yes.
Black box.
Yes. Using kind of
Find
integration.
that LS.
Right. Yeah, basically what I'm not writing here, if your polynomial is sparse, then you can learn it in poly S time. It's a result by Cleve and Spielman and others. Okay, so let's do the other thing. Let's let me have this. Oh, I'll go. So let's move on to the following model, which is so here now think of K as being very small, but now there's no condition. Here we use that Li's are linearly independent. We want to do something in worst case. So we have black box access to the polynomial f. Not right. So polynomial f, and we want to learn this decomposition. Again, if you have no assumptions on LIs, this decomposition will not be unique, but you want to find one. So how would you proceed? So we'll need some kind of
independence.
Oh, because if there is no linearly independent, then determinant of A can potentially be 0. So you will do all this thing, and then what you'll get is 0. And so, and you can do this for the general Jennrich algorithm. You can even recover for general tensors just like this. You have to come up with a different matrix than Hessians, but you can in particular recover this. For doing learning for this, we need a notion of essential variables. So let me maybe write here variable reduction. So for that, we'll need the notion of number of essential variables of a polynomial. So this is the minimum. So this, let me define it as equal to the minimum number of variables over size of variable set of f of ax for all a in GL and F. So you can apply any invertible linear transformation on a polynomial, and how many variables can you reduce to? That's the notion of number of essential variables. So some observation. So basically, if you have to so let's just observation for this model. Okay, let's just do this. What are the number of essential variables of this? So you can just count up each linear form as a different variable, and so the number of essential variables of this model less than equal to k, right? Let's just stick to this right now. And there is a result by Carlini which says that you can actually find the invertible linear transformation A in polynomial time. So there is a result by Carlini says that given F. So given means even black box works here, but given F in X. So capital X is a set of variables x1 up to xn. We can find A such that, so A is invertible such that f of ax just depend on the first number of essential variables.
Sorry, I'm getting lost.
Mhm.
So, I mean, in your last observation, you were saying that the number of essential variables of like a polynomial
Right,
is more or equal than k, and in this example above, this case like the rank of your polynomial, the ruling rank of your polynomial.
right. Because you
But there
can,
are plenty of polynomials that rank higher than the number of variables.
yeah,
What it's written there, that I don't understand.
somehow didn't get your question.
So here you wrote that the essential variables of that polynomial is the one that
Any polynomial in this class, right?
is more or equal than k.
Right.
And k is like the minimum of this ordained, right?
Oh, I see. Maybe I confused. K. So when I write k here, the summation is k many linear forms. So you can in particular apply linear transformation to send L1 to x1, L2 to x2, Lk to xk, and that reduce the number of variables to just k.
Yeah, what I'm asking that I don't understand is that I may write a polynomial with like in two variables.
Right.
So the essential variable is 2 with that k strictly bigger than 2.
Right.
Yeah.
Right. That you can do. But the point is,
And that I cannot do better. That's what I'm saying. I have plenty of examples where.
sure. What I'm saying is, for any polynomial in this class, the number of essential variables is less than k, because that's defined as the minimum you can do.
Let's say the number of essential variables is at most in the rank.
Yeah, I'm saying that examples where this is not the case, so I'm not understanding.
No,
you know,
No, but you have to put it in this class. If you are in the sum of k powers of linear form, then now he gets to pick 8. And the 8 he picks will, I mean, if you are sum of k things with the sum.
Yeah, okay, sorry,
No worries.
I'm sorry.
It can be much lower, yeah.
Yeah. I'm sorry.
And the point is, you can find that a in polynomial time in poly n.
For tensors, this is called concise sometimes. Like when you find this a, like f of a of x is like the concise version.
Concise. Oh, I see. Oh. It's a complexity of f. Okay. So it's very convenient now. So we can just work with f of ax. We'll apply Carlini. And look at f of ax. And this is a polynomial now in f of x1 dot up to xk. Think of k as a constant now. And you can just and f of ax can be written as L1 prime, L1 tilde to the d dot Lk tilde to the d, right? And these are polynomials or linear forms in just k variables. So I can just write this as a system of equations to find a representation of f. What do I mean by that? My polynomial is a degree d polynomial in k variables. So its monomial representation will have roughly n plus or k plus d, choose the elements. That's the number of monomials here. And I'll write Li tilde as in a symbolic way. I write it as Aij xj to the d plus for all of them. And I'll compare coefficients. This will give me some equations and some unknowns. My number of unknowns in this thing. So this gives me a system S, and number of unknowns in S is k times t. No, it's actually just k square, less than k square. Number of equations is this many, and the degree of each equation is less than d. So we have reduced the problem of learning the following model to a equation, to a setting of solving system of equation. So let me just talk about that problem. So suppose you have a problem which is you're given polynomials f1 up to fm in n variables. and the degree is less than d of each of them. And you have to solve, find alpha such that f1, fi of alpha equal to 0 for all I in F. So this is an instance of system solving, and let's denote the time complexity like this. Let cis nmd be the time complexity, and if your field is complex, depends on the field, then this is less than equal to or equal to nm to the order m d to the order n squared. So the bottom line is, if your number of variables that you are looking for is constant, then this is efficient, and that's what we are using here. Think of k as a constant all over, and if we have reduced by applying Carlini the number of unknowns that we are looking for to a constant, so we can directly apply system solving and just learn this representation. So this is like a very simple algorithm to do Waring decomposition. Any questions? So I'll quickly move to learning general tensors. Symmetric tensors turn out to be just one trick away, right? So you apply one trick to learn it, and leave this maybe here. So now we want to learn the following model. F can be written as, and our ideas would be do some variable reduction. The tools we have are variable reduction, but we can't directly apply Carlini because we want to preserve this structure. Oh, note that first, another observation, that what's the essential number of variables? Let's say observation 3. What's the essential number of variables of this model? Basically count the linear forms, and this will be less than k times t. So we have variable reduction, system solving. And what I want to say is, if we are looking for low dimension tensors, for example, d equal to 3, this is enough. And if you want to look at general dimension tensors, we'll note another notion called rank bounds, which we'll talk about later. But for now, just think of d as small, for example, 3. And then can we learn this model? So note that, so okay, if d is, let's say, 3, yeah, why not? Let's talk about these 3. Then your essential number of variables are small, which is a good thing. But we directly cannot apply Carlini because if you apply invertible linear transformation, it will just mess up the structure of variable disjoints, variable disjointness in the linear form. So we have to cook up a homemade version of Carlini such that it ensures that you are reducing variables while keeping the new set of variables variable disjoint. So what you can do is suffices. This is because of some variant of variable reduction we prove.
This is like, it's like a generalization of when you have a matrix, a certain rank.
Right.
And
Right.
you apply row operations and column operations.
Yes, yes.
That you have a
Yes.
non-zero, and then
Yes.
the rest is.
Yes, that's exactly the proof actually.
But now you have to do it for tensor. It's like
Yeah,
higher dimension.
yes. Yeah, so you just keep one alive, set everything else to random variable. And if this k is optimal, that substitution will be invertible, and you will keep on doing for each partition to basically reduce the variable. Suffice to learn when each. So basically that invertible linear transformation will reduce each partition size to be k. So it suffices to learn when the size of this xi is k. To begin with, it could be n, but now we have reduced the variables to k in each partition. And the total number of variables would be now k times d. Again, you can just write your linear forms here, expand it as a, think of your linear forms as unknowns, you write it, your polynomial will have f will have k to the d monomials now. So these will be your number of equations. The number of unknowns will be k times d. Again, your d is small, k times d, and degree is d. So if you set up a system directly in the low degree setting, you are again in a very good setting because your number of unknowns is constant. I'm assuming D is small. It suffices to learn the low degree, in particular the 3-dimensional tensor, assuming rank is small in the worst case. So now moving on into the high rank tensors, high dimension tensors. Let me go there. Before moving on to high dimensional tensor, we have to quickly talk about something called rank bounds. This captures the notion of if I give you a depth-free circuit, so if I give you sums of products of linear forms, and this computes a zero polynomial, identically zero polynomial, then we have results which says that this implies that the dimension of span of Lij's, that is the rank of the circuit Lij's, is small. Let's say k to the 100. So we have results of this flavor. I'm hiding some technical details here, but morally we have results of this flavor. And since we are working with this special model in which we have even variable disjointness, in this, what we get is something even more stronger. We get if then degree. So I can think of this as each term, which is I equal to 1 to k. I can think of this as T1 plus T2 or the Tk, where each Ti is just product of linear forms. This implies that degree of each Ti is actually less than k minus 2. So if you have a high degree circuit which looks like this, it can never compute zero unless some trivial thing happens if the degree is large enough.
For the pi Lij equal to I. Right. Yeah.
Yes.
Right. So we have this strong result, and this helps us to prove some kind of uniqueness. Why? Because so we have. I'm hiding some technical details. Whatever, if some sub-circuit computes zero, or if there's a large GCD, but it turns out those are the only two bad cases. So I want to say that we have uniqueness, quote unquote uniqueness, in our representation because of rank bounds. Why is that? Suppose there are two representations. Suppose you have T1 to Tk of a tensor, and also another one T1 prime, T2 prime, up to Tk prime. Then this is a top finite 2k circuit which computes the zero polynomial, and this means there is large GCD among these gates because I want the degree to be small. So if your polynomial computes zero, then it must be the case that there is a big GCD which pulls out over here, and the degree of T1 or so this implies roughly that if you have two representations, this implies, again I'm hiding some technical details, that for all I there exists J such that, or I prime such that GCD of Ti comma Ti prime is large, is greater than equal to D minus K.
So what is the GCD of the tensor?
Oh, this is not tensor. So these are products of linear forms. So the GCD would just be take out the common linear forms.
These are then rank 1 tensors. Is that the right way of formulating?
That is correct. These are rank.
So the GCD of
But these are rank 1 tensor is also product of linear forms, and I'm talking about GCD of those things.
there you want to say degree. So
Yes. Oh, yes. Degree of the GCD.
in this case, they're products of linear forms. So no matter just
So TIs look just like this. It's product of.
sorry, like you're losing me a little bit. So this first part just simply says that if the decomposition is unique, right?
Decomposition is not
then
unique.
it can't be computing zero.
No, the decomposition is not unique in these settings, right? So I want to get some kind of uniqueness because there is none right now if you don't assume any conditions. So how do we prove those things? We prove that if your degree is large enough.
But if the decomposition is unique, isn't that a statement that it cannot compute zero unless it's identical to zero?
That's correct, but it's not unique. So in worst case, tensor decomposition is not unique.
Sure.
And
But But the first thing basically is a condition that's d smaller than k-1, which says like, okay, that
This is a lemma. It's an informal lemma, so I'm just putting a star because I'm avoiding some conditions. And using this lemma, I'm saying you can prove some kind of quote unquote uniqueness. That is, if you have two ways of decomposition tensor tau, this is the first way, this is the second way, then both the decompositions, if you think that the rank 1 tensors have a lot in common. And that's just a way of writing it formally in terms of polynomials. There's some simplicity and minimality assumptions which I don't want to write, so I kind of rushed over the details. But you get some kind of uniqueness because of it.
parsing the variables for all I, there exists an I prime such that GCD of Ti and what?
Okay, so
T of I prime.
pick a T1 here. Sorry.
There is a J1, is it a J or an I?
It's I.
It says GCD of Ti, comma, and what does it say then?
Ti. So pick a Ti from here.
You can just
There will-
right? You can just write all of them.
It's the prime in one place, they probably did it.
Yeah, but it could be other one for each I.
Just make it one I name, maybe, because you can read all of them.
T prime, I prime.
T prime, I prime. Oh yeah. Oh yeah. Oh yeah. Oh yeah. That's what I meant actually.
It's really an I and it looks like a J.
Yeah.
But,
Okay. So let me see why these are useful for high dimension case. So we learned the low dimension tensor. Now we want to learn high dimension tensors.
The lemma star is easier or hard?
It's not for set multilinear circuits is fairly straightforward actually, but we have analogs of this for general, and those are really non-trivial results in algebraic complexity. But this one is you can maybe prove by induction. Okay, so how do you proceed? I'm just giving a sketch of how do we learn the high degree case. So we have, I'll call tensor but write a circuit. So that's and this J goes to 1 to D. We can't learn this, but we'll project it to a poly K. We'll project this polynomial F, which will project this circuit to some, let's say, K to the 5. This we will learn because it's a low degree setting. Because of uniqueness, this something which is of low degree have a lot of things in common with the original tensor decomposition. So what we get is by learning the projection, of F by learning F sigma, we will get a lot of things, in particular two linear forms, L x1 and L star x1 that appear in C. C is the original circuit representation of F. So if you know two linear forms, you can just go modulo these linear forms. And now you reduce your top panning. Right? So you reduce the question to a question of tensor of smaller rank, and you can get a recursive algorithm like that.
You pick sigma kind of random.
Yes, it will be random. You can actually de-randomize those randomness using PIT and all those things. But right now it's random.
And then you do the original, then you do that stuff.
So then you reduce the top panel, so you can apply it recursively. And for the base case, and the top panel is just one, it's a rank 1 tensor, you can just decompose it using black box factoring. So this gives us a black box strategy to learn it. I will not go over it into details because I want to discuss some open problem. So yeah, so basically mixing all these three ideas, variable reduction, system solving, and rank bounds, we can learn general tensors. And the time complexity that we get, just to point again, is d to the k to the order 1, k to the k to the order 1, and n. And on Thursday, Bentley will separate this k and d. Basically, he'll give an algorithm of the following form: maybe k to the k to the k to the order 1 and poly dn. So what this have additional benefits is that our algorithm for k being slightly super constant will be quasi poly, and he can get it in polynomial time. Okay, so moving on to some open problems. So first is okay. So we learned if open. What if the slice rank is constant? Can we learn it? So if tau has slice rank, okay. Slice. Can we decompose it? By decompose, I mean a slice rank decomposition. You can also ask for same for sub rank, geometric rank. I mostly thought of this. I think geometric rank can be solved because it's a system of equations and that is constant. You can solve it. Sub rank I have not really thought, but I think slice rank I've tried and struggled, and that boils down to a very clean circuit model. But again, I can't solve that. Again, also Kevin wrote about it, so it's something like this. You have a linear form X and then a quadratic form Y comma Z. Then you can have a L2 in Y and then a quadratic form in X comma Z and so on and so forth. So the variable partition gets mixed up in this model, and I don't know how to work with these things. But so I'll leave this as an open problem. So again, the bulk of this work is what can you say about tensor decomposition in the worst case? No assumption. So another thing that I would like to pose as an open problem is what's a worst case approximation algorithm for tensor decomposition. So worst case approximation algorithm. Let's say for k rank. So we know it's hard to approximate up to 1.0005, but they give me an exponential approximation. Sub-exponential.
Approximation. You mean border rank?
No, approximation give. Okay, so there exists a tensor rank decomposition with rank k, but you give me a tensor rank decomposition with rank k to the 100 efficiently. So my time complexity is k to the k to the k, but I want, if you want to do in poly k, something like that, but you give me a worse decomposition. Okay, good.
I don't understand. I simply doesn't want mathematics.
Okay, let me maybe rub this. So given tau such that rank of tau is k, give a decomposition as a sum of whatever k to the 100 rank 1 tensor.
What about the approximation things? So what about order rank? As a third open question for can you solve this?
Yeah, I didn't thought about it. So you're saying the border rank is constant, and then
I mean, learning border rank.
right? Yeah, I didn't thought much about it. But
I'm sorry, okay, so you know that you have a tensor of rank k,
right.
and you look for its possible other decomposition of with higher number of terms.
Right, but I want to do it more efficiently. I want to do better time complexity than these. I want to do like say poly k and instead of exponential and k.
And you can add and subtract the same rank one tensor as many times you want, but that's not your looking for.
Yeah, but
You're not given the decomposition into k. You're just given the sum already.
I say I will. So you have a decomposition with k to the 100 addendum, and
no, this is you know that the rank of the tensor is k. This is a promise to you. Let's say the rank of the tensor is maybe k is confusing. Let's the rank is n. So I promise you that the rank of my tensor is n. Give me a tensor decomposition. Mine would be very inefficient. Even if you give me n to the 100.
Yeah. So this question relate to what you brought into, because into you write approximation. So
Oh yeah, this is true. I rubbed this. The first is over, and I saved space. So I wrote again here.
Yeah. So the question is how the pink sentence relates to.
Yes.
Yeah. So how?
It's the same.
No, I've been looking this thing. So the big sentence is, as far as I understand, you look for a rank decomposition of your tensor, whatever it is.
Yes, the best you can do efficiently.
Yeah. And 2, you ask for an approximation.
No, I think the word approximation seems sort of like weird. I mean, the approximation, you mean k to the 100 instead of k.
Yeah.
The word approximation is used in some way,
Yeah.
which I find counterintuitive.
It-
Use some other word for it. So, what can you know? The technical question associated with 2 is given t with rank k.
Can you find the decomposition?
Can you find it? What's the best decomposition you can find in polynomial time?
Right.
Say, right?
Yeah.
And you know, concretely, you could say, can I find the decomposition of size k to the 100 in
Okay.
polynomial time?
Right. So I have a lame argument which can do k to the d. So it's I mean it's very lame.
Yeah.
Very good. I mean, for d smaller than 100, you're
Yeah. Yes. Yes. And I want to beat it though. Yeah, those are the two open problems I would like to leave. And that's it. Questions?
Questions?
I have only more remarks. The result that you quoted at the meeting. I think we should also quote European and Canada. I think it's assumed there that it's much older than the anime result.
What's the name?
Yarobino and Canada.
Okay.
So it's a book.
Okay.
These are the two authors,
Right.
and I think it's already there.
All right. Yeah. Thanks.
Just confused. So this you call rank bounds, this lemma, I must start.
Yeah, it's for some other because it's rank. It's I mean originally it's for we want to look at dimensions of span of LIs. So it's we call this thing rank of the circuit for depth circuits, and that's why it's called rank bounds for some reason. Yeah, it's not the best name in this context.